All right, let's get started. Okay, so the agenda for my talk is talk about what cuQuantum is and what it's not. And then I'll introduce two libraries. We'll start with a state vector library, and the second one is a cuTensor net library. And then we'll talk about how you can work with cuQuantum, how you can obtain it, and what we're planning to do next. All right, so researching and developing the computer of tomorrow, which is quantum computing, that'll help accelerate all of computing, will require powerful simulations today. And I tried to illustrate this in a chart. Don't get hung up on the numbers, especially the QPU numbers on the bottom left. This is a log-log chart that I put together. The y-axis is circuit depth, and the x-axis is number of qubits. And the purpose of the chart is to kind of differentiate between where state vector simulators and tensor network-based simulators play a role, and actually visually illustrate that they enable algorithm development research, which was the title of this talk, beyond what QPUs are capable today. Given the error rates and number of qubit limitations on actual QPUs, which again, this picture is not 100% accurate, especially on the y-axis. The 127 is the latest IBM Eagle. You can see that for error-corrected, fault-tolerant logical programming of quantum computers using tensor networks or state vectors, you can build algorithms and do that research and development today. Okay? The data points that I'm showing are actually a lot of the benchmark results that we'll show throughout the talk. And my colleague, Sam Stanwyck, our product manager, has already shared a number of these. You can see, for example, our results for the max cut problem going all the way up to 5,000 qubits. And then the RQC is from the Gordon Bell Prize-winning paper that solved the M40 random quantum circuit. And then you'll see some VQ results and some others. Okay, so this sets the stage for where quantum circuit simulation plays a role and why we're trying to accelerate it with libraries. So what is cuQuantum and how will it help you accomplish this goal? It's a set of optimized libraries that are designed to accelerate quantum computing workflows. And for starters, we're trying to tackle the problem of simulating quantum circuit simulation, right? Before I get into the diagram on the right-hand side, the block chart that kind of illustrates where the SDK fits, cuQuantum is not a quantum computer, it's not a quantum computing framework, and it's not a quantum circuit simulator itself. We talk about state vector simulation and we talk about tensor network-based simulation, but we actually don't build the simulator. We build the libraries that accelerate it. This is analogous to how libraries like cuDNN and cuBLAS accelerate deep learning frameworks like PyTorch and TensorFlow, which accelerates deep learning, okay? So the picture on the right-hand side tries to add some more definition and clarity to this. On the top, you have the quantum computing application. Then you have the frameworks like Cirq and Qiskit and many others. And then you have a choice of running this on a simulator or a physical quantum processing unit shown as the yellow box QPU. If you go down the simulator route, that's where you get into Qiskit Air or QSIM and many other simulators. And cuQuantum sits right under them with its state vector and tensor network, and in the future, probably other libraries. And that opens the door to doing GPU-accelerated quantum circuit simulation, as shown here. Okay. So let's start with the state vector simulator. Okay. The state vector simulator, as the library, the goal is to accelerate software stacks that are using the state vector method to simulate a quantum circuit, noisy or not. You'll see this library actually has no notion of whether it's simulating a noisy circuit or not. We try to provide APIs that try to do the mathematical operations as fast as possible on GPUs, and then we expect the simulator and the framework to take advantage of that to do the research and algorithm development. That's an important thing to remember. So you'll see, the one thing that we don't have control over is We don't even own the state vector memory object. I put the API here just as an illustrator for the gate application matrix. It actually has no notion of gates, right? You can provide your favorite gate or whatever's coming up in your circuit and formulate the matrix the way that you want. So it's trying to be as flexible as possible, where the circuit simulator owns the memory for the state vector. It's prohibitively large, so we can't really afford to make copies, right? And the framework will want to own that kind of memory management. If you're in software, this will make a lot of sense to you, especially dealing with large memory chunks. And the second part is we want to enable things like gate fusion. So the matrix can be larger than the typical sizes for just one or two qubit gates, right? So we have some common use cases that we covered with the first beta release that's already out, and we'll cover that at the end. And we're adding more with the second beta release that's coming out very soon. I'm not going to go through these one by one. The key thing to note, and I'll mention this at the very end again, is to give us feedback. What are we missing? And what could we do better, and how can we change our APIs to kind of serve your needs, okay? Because that's our goal with these libraries. So people are usually interested in like performance numbers. What will I get if I use the cuQuantum libraries in my simulator, right? So all the results obtained here for the GPU are on the A100 GPU, the Ampere architecture GPU with a 80 gigabyte memory, so it has 2 terabytes per second memory bandwidth, and a lot of the quantum circuit simulation applications are memory bound, so that's an important factor to remember. And then the comparison is made against a 64-core state-of-the-art CPU. So the left side is one 64-core CPU versus one 80 gigabyte A100, right? Same thing on the right-hand side, but it's specific to VQE. We'll get to it in a second. So the y-axis on this chart is the speed up, and the x-axis is the number of qubits. And as we grow the problem size, you get to the point where you're starting to see very, very significant speed ups, often exceeding 10x, 12x, and for the Shores example, you can see we hit close to 19x speed up on a one-to-one comparison. This was done using cuStateVec accelerating circ and QSIM, and it's available for download. The right-hand side chart is showing 4 different molecules VQE simulation and the speedups obtained in that case. Again, we see a very similar speedup in the maximal case for ethylene, where we have a 22 qubit simulation and a 19x speedup over the CPU. And we hope this illustrates kind of the purpose of these libraries to provide drop-in acceleration for simulations that normally take a lot of time. Okay, multi-GPU. So this is where we go from having a single GPU on let's say, a workstation or on a cloud server instance to a multi-GPU system. And the system, not surprisingly, that we pick is the Nvidia DGX systems that have 8 GPUs per node. And these systems have Nvidia's NVLink and NVSwitch that connect the GPUs together with a very, very high bandwidth and low latency. And that's what we're trying to take advantage of. And the left-hand side is showing a strong scaling study for the same benchmarks you saw on the previous slide, where we go from 1 to 8 GPUs. You see the expected speed up would go from 1 to 8. And even in the worst case, we get over 50% parallel efficiency, getting about 4.6 speed up for the Shores. And that's constantly improving. And then you can see close to ideal speed up for the rest. If you're wondering how this compares to CPUs, we try to make it a different kind of comparison on the right-hand side chart, where the x-axis, again, is the number of GPUs and y is speed up. But this time we're talking about comparing to on a server with 2 sockets. If you were using all 128 physical cores, how would using a DGX compare to that if I was running my workflow? And you can see in the maximal case for QFT, you can get almost like 90x speed up 8 GPUs versus a 2-socket CPU server. So these will continue to improve. The benchmarks will grow, but this is the kind of potential that GPU-accelerated quantum circuit simulations will provide. Okay, let's move on to tensor networks. All right, so if you know nothing about how tensor networks are used in quantum circuit simulation and why this library even exists, hopefully you get a sense of what's important and why we're trying to do it. Happy to talk later as well. There's a lot of literature, and it's a very active area of research, and we're finding new things every day, but it really opens the door to a very large number of qubit simulations. So it's a critical element for us and for quantum computing in general. So this library, as stated, will accelerate tensor network-based quantum circuit simulations, right? It actually, again, has no notion of what it's doing. It looks at tensor networks as generic tensor networks. It's just a bunch of n-dimensional algebra objects that need to get multiplied together. The example on the right-hand side shows you can do that in a naive way, or you can be really smart about it. And everybody here should have basic linear algebra to understand that if I was doing these vector products, right, A, B, C, D, E, and I just go left to right by doing this red box first, then this red box, and then use the product to multiply the last one, I actually end up with two matrices in the middle that then turns into a matrix multiply, and then end up with 2n cubed plus a second order term, but the third order term is 2n cubed, right? On the right-hand side, if I actually choose to do the rightmost dot products first, it actually turns into a vector scaling, and I have linear cost. It's just 6n, right? Now, this is very easy for this example, but if you turn your quantum circuit and you say all the gate matrices are tensors and consider the number of qubits and the connectivity involved, this becomes a very complicated graph. And as you contract, the tensors get bigger and bigger and bigger. So you actually need very clever algorithms that order the operations such that you do the minimal number of flops. And that's what this library does for you, exactly. It first calculates an optimal path to contract, then it creates an optimal execution plan, and then it actually executes those contractions using Nvidia's pairwise contraction library called cuTensor. All right, so let's look at some results. Before we get into the results, I will very briefly talk about the complexities involved in the ordering process. So, like with any NP-complete problem, there's a lot of heuristics involved, and this is one of the biggest areas of active research in tensor networks, where you have to develop some kind of optimizer that looks at a tensor network and then applies a bunch of methods to it and try to converge to an optimized path, right? We talked about the max cut problem. All those optimization problems require some kind of iterative process and heuristics to get to a reasonable solution. Finding the optimal solution is often out of the question, right? So the first thing we do, optionally, is do a simplification. And if you read the literature, especially the literature from Stefan Cortis and Johnny Gray from a library called Cotengra, and the QUIM library from Caltech, it's a great resource and the state of the art as far as generic tensor network optimization is concerned. So simplification looks to find low-hanging fruit and removes them before, like if you had a very complex graph, you can simplify it first and then try to tackle the hard part of the problem. Otherwise, your heuristics get really confused, right? So then you have this hyper-optimization loop. And this is where your time budget comes in. You can keep searching this infinitely large space for a good solution. And in doing so, you keep repeating these basic operations where we take the graph, we split it into pieces, we split them small enough that we can use an optimal ordering like opt-einsam. And then we use that same algorithm hierarchically going back in the partitioning and put them back together. And it turns out, in some cases, you end up with contractions so large, they don't fit on a GPU. Actually, they wouldn't even fit on a supercomputer. So then you have to do some trickery. It's called slicing and reconfiguration. You say, I'm going to do a lot of extra work, but I'm going to cut it so that this repetitive work requires the reduces the maximum memory required so it fits on my computer. So there's this trade-off between space and time that's constantly going on. And it's an optimization loop. There's a trick called reconfiguration to kind of look for rearranging some of the trees that show up in the graphs. So there's an iteration here, an iteration here, and then at the end you get an optimal path. And that makes something unsolvable to hard to solve to, it's actually quite easy to solve. It makes a dramatic difference. The cuTensorNet library will expose all the parameters that you need to tune this. It has defaults that we've been setting with the benchmarks, but it will provide a way for you to actually do research with this library and try different parameters when it comes out. Okay, so I have about 10 minutes left. Is that right? Okay, so let's look at some impact performance, right? So these are some preliminary results, and we're looking at the random quantum circuit, the Sycamore supremacy circuit, with different amount of depth. The M shows the depth measure. The actual depth is 2 times this number plus 2. It's the front and end Hadamard gates plus 2 times the size of the circuit in between. And then the numbers in the parentheses are the number of tensors that were in the graph. Post-simplification, there were actually many more, but after we simplified, we were able to bring them down to this. I don't show you what the naive optimization, flops are. So the y-axis here is your total cost. And the way that's measured is how many floating point operations do I have to do to calculate the final result of this tensor network. And if you're familiar with tensor networks, I had this equation on the first slide, and no presentation is complete without an equation, right? If you have like your starting state vector and your expected state, and you do the full contraction, you get the probability of finding that in your final state vector, right? So that's that total cost to just calculate, let's say, one amplitude. And if you did the naive thing for some of these circuits, these e to the power numbers are in the thousands. There's no computer in the universe that can even do it in the time the universe has existed, right? So you have to do something smart. And this shows how much this can impact you. The black is Op9sum's auto, and the gray is Op9sum's auto HQ, which tries to do an improvement. And then the orange and the green are comparing Cotangra and cuTensorNet. And we consider Cotangra to be the state of the art. And if you're interested, the references are provided here. So if you just use Op9sum for your tensor network, you're close to e to the power 32 flops. That's a lot, right? And then if you say do a higher quality, use different heuristics, you can bring that down to 25. Where actually, if you do use Cotangra or cuTensorNet, which have very comparable performance, is you get down to the e to the power 18s, which if you have a petaflop machine, now things start looking like this is doable, right? So you go from the impossible to possible. So that's an important takeaway message. And one of the other things that we're trying to do is to calculate these as fast as possible. Although I should say, if you're going to do many, many, many contractions, sometimes the cost of the calculating the order is easily amortized. Okay? Now let's look at how fast we can actually do the contraction. What do GPUs bring to the actual contraction process? So the y-axis is speed up, and the x-axis is 4 different models. And I tried to keep the colors the same. So gray is Op9sum, orange is Cotangra, and green is cuTensorNet. Now this chart needs a little bit of digesting. What we're showing is the speed up of doing GPU-based tensor contractions for the entire contraction process versus doing them with cuTensorNet, which relies on cuTensor. So we have an optimized pairwise contraction library, and then we have a library that uses the one it depends on in a very optimized manner. There's some things we can do to plan things so that it runs even faster, right? And the different bars are using different orderings. So normally you would say, well, if you're just changing the bottommost implementation of how the pairwise contractions are done, regardless of the ordering, I would expect to see like similar speedups. But it turns out that Cotengra and cuTensorNet actually generate orderings that are favorable for GPUs where they're more compute intensive. And OptiSum seems to be in multiple cases creating orderings that are less favorable for GPU acceleration. But at the end of the day, what this library gets you over CuPy, which is a well-developed GPU-accelerated library, but not using cuTensor underneath or cuTensorNet, you can get a very large, another order of speed up on top of like a good ordering. So the message is there's a lot to gain from a better ordering and a better execution library, which is what we're trying to deliver to accelerate these applications. All right. And the last results slide, Sam covered this in a lot more detail, so I have a very, very brief slide here. But for those that missed it, I'll go over it very quickly again. There's a paper out there that came out earlier this year about doing variational quantum optimization for the max-cut problem using multibasis encodings. The multibasis encoding allows us to solve a number of vertices problem with half the number of qubits. So when you see 1,688, that's actually a 3,375 vertex max-cut problem. And we built a software stack using cuQuantum, which does have some unreleased features that were used in this benchmark and will likely be released in a future release. But it relies on cuQuantum, an open source software framework called TensorQuantum, and PyTorch. And we put all of this together to run on Nvidia's Selene supercomputer using close to 1,000 GPUs. And what we were able to accomplish is run the largest Tensor Network simulation for the max-cut problem using a quantum algorithm. Of course, the goal here is to show that you can do the algorithm development. If you ask how long this runs, it's going to solve it a lot slower than a classical algorithm and a lot slower than what a quantum computer will eventually do. But that's not the purpose. The purpose is to show that you can actually scale these algorithm developments and debug them and see how they work and how they behave. This is an iterative converging algorithm, so it gives you a lot of interesting information about the number of layers you need in the circuit to get convergence. For example, the result that we show here achieved 97% convergence. And we have a run with 5,000 qubits for a 10,000 vertex problem. That only converged to 93% in the amount of time that we had to do the study. And of course, that can be improved in the future, but it just shows you the iterative nature of algorithm development and execution, and doing this way ahead of the time where such a quantum computer will be available to run this. Okay? All right, so what's next? This may be the part that you're most interested in. So the public release of cuStateVec has been available since our GTC conference a few weeks ago. It currently accelerates Cirq. You can download Cirq with a cuQuantum plugin, and you can get cuQuantum and get this acceleration for your state vector simulations. And then Qiskit and PennyLane are forthcoming. We have another beta release coming out very soon. It will add the grayed out cuStateVec APIs that I showed earlier. It will add the cuTensorNet library with all the performance characteristics that we talked about. And one of the most asked features, it will provide Python APIs for everything. The Python APIs will be on CondaForge and on GitHub. And we hope that enables a lot more people that don't have C++ libraries that can only use the underlying libraries. So we're hoping to enable all the people that work in Python these days. And that should make life a bit easier. And then the plans for the multi-GPU portion, so all of the items here our single GPU. For the multi-GPU results that we showed and the multi-GPU DGX system that we show on the right-hand side, the plan is to have containers available on Nvidia GPU Cloud where you can download. And if you have access to a multi-GPU system, you will get kind of a container that's turnkey with a multi-GPU accelerated simulator based on Cirq, and enjoy the speed ups that we have shared earlier. And that will continue to extend as well. As I mentioned earlier, the most important thing is please go ahead and try cuQuantum if you're interested, and please give us feedback. Like, this is a brand new library, it's in beta form. The more feedback we get, the better products that we can build. You'll find bugs, you'll find performance issues, you'll find missing features. We want to hear that. If we hear it, we can make it better. So thanks in advance for sharing all your feedback and listening to me. And I'm happy to take any questions that I'm able to answer. Thanks. It is hot on stage.
Qiskit is coming. Do you know when it will come out, and is it available to try it now in a beta version or something?
I think it's planned for December,
Okay.
but all plans are subject to unforeseen delays. So there should be we're expecting a Qiskit update that provides a cuQuantum integration. The Cirq one is already out. The Cirq QSIM one's already out. Other questions?
What would be the requirements for running it? Do you even have a GPU, or is this something that you handle?
Oh, great question. Okay, so the question was, what are the requirements for running it? And I think specifically asking about like what type of GPUs you can run it, whether it will run on consumer grade GPUs. Not surprisingly, a lot of our optimizations and testing are on server grade GPUs, as I showed. But there are workstation GPUs like the A6000. So I should start with the support promises. Volta and newer GPUs are supported. So you can use Volta, Turing, or Ampere. And it should work on any consumer grade version of those, with possibly some exceptions on the Turing boards for laptops. I mean, there are some very customized ones for the gaming and low-cost laptop industry. So there's no way to kind of optimize for those, right? But Volta, Turing, and Ampere are supported, workstation grade, and it should work. But that's not where we optimize performance for. But it kind of goes with we used to be called Quadro series GPUs are going to be closer to the data center ones, and as you go further away and towards like RTX and GeForce, you're going to find less optimizations. Yeah, but you can get started and working on it. You may debug it, etc. Yeah. Yeah. This one, yeah. So that one shows that there's a saturation happening. So as your problem gets bigger, both the CPU-based simulator and the GPU-based simulator, so I should repeat the question, why isn't the QFT on the slide not showing increasing speed up? This doesn't mean the simulation is not running faster and faster. It just means the relative ratio is not changing. And that means both of them are kind of saturating, say, at like a constant factor, like the memory bandwidth of the CPU versus the GPU, times some multipliers. And once we hit that, it can no longer provide like an extra speed up as you keep growing the problem. Because you're limited, the speed up is now limited by hardware properties, if that makes sense. Hardware properties times some implementation. If the actual simulation time keeps going down, it's just the CPU is also going down, and that ratio is staying constant. I hope that answers the question. But that's not the case for the others. So there's still room to go, and they will hit that eventually. Okay, I think we're out of time. Thank you.